Hello. Yeah, I want to talk about the couple of discrete distributions. In this lecture, specifically the Poisson distribution, and give you just a quick example on the hypergeometric distribution. Start with the Poisson distribution. The Poisson random variable, which gives rise to Poisson distribution, arises when you count the number of events that occur in an interval of time when the events occur at a constant rate. Examples of that, like arrivals at an emergency room, number of items demanded from a store shelf or an inventory, number of items in a batch of random size, number of arrivals at a bank teller system. Other examples, number of accidents that involve alcohol, and so on. So these would be examples of a Poisson distribution. So if you have a random variable x which has a Poisson distribution, it's going to take this. The formula would look like this one here. The Poisson has one parameter versus the binomial which had two parameters, n, number of trials, and p, the probability of success. In this case, the Poisson has only one parameter, lambda, which turns out to be the mean. And so if I want to calculate p of x, it's going to be e, which is an irrational number like pi. I give you an approximate value of this in a minute, raised to power minus lambda, lambda raised to power x over x factorials. And the possible values of x range from 0 all the way to infinity, because as you get larger and larger x values, the probability becomes smaller and smaller, as you can see here. So here's an example of a Poisson distribution, and the probabilities are really the heights here. So the probability of x equals 0 is about 7-8%. That's x equal 1 about 20%, x equal 2 about 25%, and then x equal 3 about 20, x equal 4 is about somewhere between 12%, and then you go here, x equals 6 is less than 5%, 7 goes very small, and it goes quickly very close to 0. So for x equal probably 20, it's going to be 1 over a million or less than that. Okay. So what's this number e? Let's go and see what that number e is. That's the number e. It's approximately 2.718. It's on your calculator, so you only click on e and you get it on the calculator. You can do whatever you want with it. But if you have to use that, that's what you have. And it's like pi, those digits never ending. It goes all the way to infinity. So the mean of this distribution is lambda, the variance is lambda, and the square root of lambda. Okay, so let's talk about this example here. Now suppose the number of typos on a single page of a new book that you are reading has a Poisson distribution with parameter lambda equal half, which means someone goes over these new books and sampled 100 pages and found out there are 12% of the time no errors, 20% of the time there's one error on a page, and so on. Like follows this shape, which we call the Poisson shape. So you're looking at a page and you ask yourself this probability question. What's the probability there's at least one error on that page? It means one or more. So if we take the random variable x and say, let this denote the number of errors on a single page, then I'm looking at the probability of x greater or equal to 1, because that means I need to calculate p of x equal 1, 2, 3, 4, 5 all the way to infinity and add them up. But if I use the complement of that, because the area under this curve is always 1, if it's a probability distribution, then if I compute the probability of 0 and take 1 minus that, it will give me that sum. So that's what we have here, 1 minus p of x equals 0. And if you use the formula this will give you e minus half, and then use your calculator would be 0.395. So let me show you where do we get p of x equals 0 here. And we go to the tablet, and so I click up there and see. So I want the probability of x. Let's remember this is equal to e minus lambda x over x factorial, and now I want the probability of 0, so that's going to be equal to e minus lambda is half raised to power 0 over 0 factorial, and we know that 0.5 raised to power 0 is 1, and 0 factorial is 1, so that's really nothing but e minus 0.5. Okay, so that's what we have here. Go back to problem we have. The nice thing about the Poisson distribution is we can use it to approximate binomial probabilities, and it's a very good approximation, but it works only if n is large in the binomial distribution, so we have a large number of trials, and p, the probability of success, is very small, so that the mean mu equal np is small, so that it's usually less than 7. In that case, we can use this approximation. Let me illustrate that, and this is useful because in the Poisson you don't need to use binomial Poisson tables, although there are tables, versus binomial where tables sometimes are needed. So suppose the probability of an item produced by a certain machine will be defective 0.1. So that's the probability of success, 0.1. What's the probability that a sample of 10 items will contain at most one defective item? At most means either 0 or 1. So what I'm looking for is probability of x less or equal to 1, p of 0 plus p of 1. And let's compute that both ways, using the binomial distribution, using the exponential distribution. The Poisson distribution, and then compare the answers. And this will be a good practice for these distributions. So this is the binomial. My parameters are n equal 10 and p equal 0.1, and I want p of 0, so that's going to be 10, 0, choose 0, 0.1 raised to power 0, 0.9 raised to power 10, and p of 1 is 10, 1, 0.1 raised to power 1, 0.9, the cube, raised to power 9, and do my computations using your calculator, simplify, and you'll get 0.7361. Now, using the binomial approximation, since NP is the mean, that's going to be lambda, because lambda is our mean, and that's going to be 1. So let's compute p of x less or equal to 1, which again will be p0 plus p1, and that will turn out to be e minus 1 plus e minus 1, and you add them up, and that will be 0.7358, which is very close to this answer. Let's see how we use that. Let me go to the tablet. So now I have, in this new example here, is my lambda now is equal to 1, and I want p of 0, which is equal to e minus 1 raised to power 0 over 0 factorial, and of course 1 raised to power 0 is 1, 0 factorial is 1, so that's e minus 1. I want p of 1, and that's gonna same, e minus lambda is e minus 1. Now I want lambda from the formula up there, raised to power 1 over 1 factorial. Again, 1 raised to power 1 is 1, 1 factorial is 1, so that gives me another e minus 1, and I want to add these two together, which what I have here. Now you use your calculator, find e minus 1, or actually just maybe go back, e minus 1, also you can compute that as 1 over e, right? So that's the same thing, and add them up, and that should work fine. Okay. The hypergeometric distribution. The hypergeometric really arises when one selects a random sample of size n, say, without replacement. So you have a box, or we talk about from a population of size n. When the population has two groups, either success or failure, we call them in this case first kind and second kind. So you have d elements of the first kind, n minus d elements of the second kind. And the scheme is called sampling without replacement from a finite dichotomous population. So if you sample with the replacement, you will get the binomial distribution. So let's talk about this. So this is an example with, about sampling without replacement. So suppose a box contains 10 red balls and 15 white balls. A random sample of size n, which is 8, without replacement is drawn from, and the number of red balls is denoted by x. Then we want to find out what's the probability we have x, small x, of red balls. So, and you can see that basically we can go to the chapter of probability and compute the number of points in the sample space. So I have a total of 10 and 15, 25 balls. I want to get 8 of them. In how many ways I can select 8 balls out of 25? That's my total number of selections. And now I want the event in which 4 of the balls selected are red. So how can I get 4 balls? Well, I have 10 in the box that are red, and I want, in how many ways can I get, say, 4 of them, or x of them? Think about 4, because that's my example here. So that x would be 4, and if I get 4, how many would be left? That means the white balls, I need to have 4 white balls, or 8 minus 4. So out of the 15 white balls, so that's 15, choose 4 here. Okay, and that's how you compute that. And so I can vary 4 can be 0, 1, 2, 3 up to 8. So as you vary 4, you get that full distribution, and that gives you the general formula for it. So n, you choose n, and out of those n you want x red and n minus x from the white balls. And the mean would be, this would be the mean and the variance of for this distribution. And that's how I don't want to say too much about it, but I want to go back and show you how do you write this down for computing, say, 4 balls. Okay, so we have, remember we have 25. Let's go to the tablet, clean it, and now I want to compute I want the probability of 4 red balls. Remember I have 25, and I want to select out 8 balls. That's the number of ways of doing that. I have 10 red. I want 4 out of those 10 to be red, and that gives me, so I picked 8, and that gives me the remaining ones are going to be 4, and these should be selected out of the 15 white balls. Okay, so now how do I compute this probability? I'm just going to help you out expanding it. You can use your calculator to get those combinations. There are calculators that can compute the full range of these ones, or if you expand it and use factorials, you can do that as well. So if you do that, you're going to get here 10 factorial, that's this term here, 4 factorial, 6 factorial. I'll multiply that by this term here, which is 15 factorial over 4 factorial, and that's going to be 11 factorial. And down here I'm going to have 25 factorial over 8 factorial, and that would be left what, 25 minus 8, 17 factorial. So that's quite, so one way, first simplification is I want to put these together, this times this over this times this, that's how we can simplify. And so I'm going to have this long line, so that's 10 factorial times 15 factorial times 8 factorial times 17 factorial over 4 factorial times 6 factorial times another 4 factorial times 11 factorial times 25 factorial. Of course you can simplify further or just use your calculator now and get the answer. So you need a calculator to get the answer for this one. And I want to leave that for you to experiment with, and that's it for the hypergeometric. Okay, take care.